Hi, this is Daesol from SNU in Korea, and I will present the S2P state-conditioned image synthesis for data augmentation in offline RL. Recently, offline RL, which tries to deploy pre-recorded datasets without online interaction, has shown great progress. However, it still has a struggle to generalize beyond the given offline dataset, which is called distributional shift. To alleviate it, model-based algorithms in state domain, which run a dynamics model and augment the dataset with generative state transitions, have emerged as a promising paradigm. However, when it comes to the image domain, there is still no augmentation strategy to mitigate the aforementioned distributional shift. So, as shown in this concept figure, we try to extend the given offline image data distribution by virtually exploring the state space and generating the image transition data. Even though some prior image RL methods can be exploited for generating image transition data in a similar manner to the state-based ones, the quality of the output images from these approaches is not that satisfactory because these only exploit image input and make the generative model fail to capture the accurate dynamics and the details of the agent. Therefore, we propose S2P, which utilizes multimodal input to synthesize the realistic image from its corresponding state. This multimodality of S2P makes it possible to generate dynamics consistent images from the reliable state transitions while preserving high-quality image generation capability. This is the overview of S2P architecture, which synthesizes the novel image observation with the previous image and the current state of the agent. Modality-specific encoders project inputs from different data dimensions to the latent space. The projected latent vectors propagate to the S2P architecture to synthesize the current images. We additionally map the state vector to the disentangled latent space using the state latent mapping function to feed them with conditioning images to the MAT module. A novel MAT module is designed to effectively fuse the spatial and state signals for generating high-quality images. First, the size state vector is expanded to the same size as the conditional image, and they are concatenated channel-wise. Then, the multimodal feature extractor produces the scale and the bias vector for learnable affine transformation. Lastly, the normalized features which propagate to the generator are normalized and transformed via multimodal scale and bias. The overall training process are summarized in this algorithm. Given the offline dataset D and some rollout distribution eta in state domain, we train the dynamics model that predicts next state and reward given the current state and action, and train the image generator with the offline dataset D. Then we obtain state trajectories by using the rollout distribution and dynamics model. After that, we obtain trajectories in the image domain from state trajectories by utilizing the trained S2P generator. And we apply any offline RL algorithm with the dataset sampled from the original offline dataset and dataset generated by S2P generator. To validate whether the S2P can help improve the offline RL performance, we evaluate our algorithm with the recent offline RL algorithms in DM control environments. Overall, the offline RL results with S2P achieve better performance than the naive offline RL as shown in the bolded scores. To show why the multimodal inputs are necessary for augmenting the image transition data, we compare S2P with the Dreamer, which only uses unimodal inputs. Even though the Dreamer saw more previous steps images compared to S2P, it still has difficulty in generating accurate posture, and the offline RL performance of the Dreamer-based augmentation is lower than that of S2P. Therefore, it supports the S2P's advantages obtained from multimodal inputs. We conducted an ablation study to investigate how each input in S2P generator works. When we mask out the position of the state, S2P cannot capture the posture of the agent, but it captures the velocity by generating the change of the backgrounds. When the velocity of the state is masked out, S2P still recovers the posture of the agent, but it works in place without moving forward due to the missing velocity. Without the previous image, S2P recovers the posture of the agent plausibly, but as it cannot access to the previous image, the background cannot be reconstructed. Thank you for listening.